Look at the sheer mass of India's Parliament building. Millions of tons of stone, concrete, and steel pressing down into the earth. Building on this scale requires fighting gravity every step of the way, and the temporary structures holding these monuments up must bear an immense, unforgiving load. When a worker is standing 50 stories in the air, the only thing sitting between life and a lethal drop is a few inches of hollow metal. Gravity doesn't give second chances. IS 2750, 1964, is the mandate from the Bureau of Indian Standards. It functions as an absolute rulebook for an elimination trial. Any piece of metal failing the tests in this document is banned from the build site. The primary contestant in this arena is the heavy-class seamless steel tube, specifically one with a 40mm nominal bore. A nominal bore is the standardized internal diameter of the pipe, ensuring every tube fits perfectly with universal connectors across the entire grid. These tubes, and the joints that lock them together, have to prove they won't buckle, snap, or slip. Only the components that survive this physical gauntlet earn the right to protect the lives of the people building the nation's skyline. The first major point of failure in any scaffold is the right-angled coupler. This is the heavy steel clamp responsible for locking a horizontal tube to a vertical tube at an exact 90-degree angle, creating the core structural grid. In the distortion test, a vertical tube is secured and a horizontal tube is clamped to it as a cantilever. A 3-ton load is dropped onto the suspended tube. If the coupler bends or shatters under the weight, it is eliminated. Then comes the rotation test. The coupler is locked down, and a violent turning moment exceeding 3,220 kg-centimeters is applied to the horizontal tube. A turning moment is the rotational force, or torque, trying to twist the clamp entirely off its axis. Passing both of these physical extremes guarantees that the core grid of a scaffold won't share apart when thousands of pounds of workers, concrete, and heavy tools are piled on top of it. To prevent the entire structure from leaning or collapsing, builders integrate diagonal bracing. This requires the swivel coupler, a specialized joint designed to secure tubes at unpredictable angles. In the slip test, a swivel coupler connects a vertical and diagonal tube at 45 degrees. A 1.25-ton load drags downward, attempting to pull the vertical tube through the clamp. To pass, the tube cannot slip and the clamp cannot rotate past 10 degrees. That strict 10-degree limit is crucial. If a diagonal brace slips any further than that, the scaffold loses its lateral stiffness, making it highly vulnerable to a catastrophic collapse the second high winds strike the construction site. All of those perfectly locked joints eventually route the entire cumulative weight of the steel straight down to the ground. That brings us to the very bottom of the structure, the adjustable base plates. These plates are formed out of mild steel, a low-carbon steel that is tough but ductile enough to bend rather than snap, and they must be at least 5 millimeters thick with a perfectly level surface area. The ultimate foundational trial for these plates is purely compressive. The adjustable shank is extended to its absolute maximum height, and a crushing 6-ton load is dropped straight down onto it. What makes this exceptionally difficult is that the top of the shank is left completely unrestrained during the test. There is nothing holding it steady while it attempts to bear the weight of 3 cars pressing down on a single point. If the base plate warps or the shank buckles under those 6 tons, the foundation is compromised. A failure here means the entire towering titan above it is doomed from the ground up. Once these individual pieces, the heavy-bore tubes, the right-angled couplers, the swivels, and the base plates, survive their respective trials, they lock rapidly into a massive, rigid, 3-dimensional grid. The combined strength of these surviving components creates what engineers call a unit-frame put-log scaffold. A put-log scaffold is a temporary structure that derives part of its support directly from the permanent building being constructed. Because of the rigorous testing outlined in IS 2750, every single microcomponent in that frame has been pushed far past the normal environmental limits it will actually face on the job. Look at the heavy stone and intricate details of the Secretariat building. Long before the final bricks were laid, the sheer weight of structures like this relied entirely on the integrity of an invisible, temporary steel skeleton. When workers are suspended hundreds of feet in the air, their safety is never an accident. It is the deliberate, calculated result of an unforgiving trial of steel.